To get to a couple of things. One is if you have questions, comments, reference, request after yesterday's class. The second one is, as we mentioned yesterday, there are two topics that I was thinking of going through, and I think we go through both of them. And one is the data flow analysis and data flow testing, and another one is functional testing. I want you to understand which you prefer to deal with it first. Doesn't mean that we will not do it both. We may probably not, but we give priority, not the exclusive choice. Okay. So since you are less and you only have two choices, you may actually be lucky than listening. Okay. So topics are data flow analysis and testing, first topic, or functional testing, second. Who is for data flow analysis? Who is for functional testing? And the others are okay. Hard. Different questions. Who is for a more mathematical and formal approach, and who is for a more informal and engineering approach? Who is for the mathematical approach? Engineering and formal? Okay, that's Now, don't expect some mathematics. When I say, because I guess, you may be biased by Natasha. It's not the kind of approach that Natasha has, but I expect she has it in her presentations. So, why don't we okay, I think I can actually start now because I have a whiteboard. I don't think we should actually be sort of constrained by the availability of the projector. So I probably follow the path that I actually have on the slides anyway. So let me start. Okay, so data flow analysis, that's the topic of today. Okay, questions. How many of you know data flow analysis? Okay, that's fine. No, but that's because let's understand where to start from. So let me start with a very simple thing: control flow analysis. Okay, how many of you know control flow? Probably all of you. So the idea is very simple. You get a program, and you want to model some relation among the actions you do in the program. So you can see the program as a set of actions, a set of statements. And control flow is a very simple way of capturing the relation, some of the relation among statements. So the idea is, once something comes before, something comes after, something comes, you have a choice, sometimes you don't have a choice, and that's a fairly common way of representing a program. Actually, when I teach, I almost never write code. I actually usually prefer to give a control. Now, when you do data flow analysis, what you do is you consider a different kind of relation between statements. And now I really wanted to have the projector because I wanted to show you the flow. So let's say I have one kind of relation which is you come before. Okay, so statement A. So you have, and again, I want to say statement A, and then statement B, and then statement C. Okay, and this is the control flow relation. Now if I say something like this statement, I assign some value to X. Let's say that this is actually a very stupid thing, Don't write the score actually, but let's get it like in this way. Okay, so for some reasons I decided to, I have three state variables and I increment the three of them, in a row. Okay, what is the relation between these three statements? Nothing, exactly. So the idea is these three statements are completely independent. The relation is simply, let's say, constrained by the way we write. Since we write top down, this comes first, this second, and this third. And in the program, they would actually be sorted. And so if you look at the control flow relation that you say, oh, you do this and then this and then this. But in terms of actual execution, these three statements can be actually mixed in sorted in many different ways, right? So you don't really have to execute them in any specific order, okay? So what happens is that basically when you look at these statements, what you do is, what if I have a parallel machine, and this is actually where data flow analysis comes from. What if I have a parallel machine, let's say I have a multiprocessor, the classic, you don't have to think about this huge scientific computing machines, just, that kind of stuff has a couple of processors running, or even a pipeline execution. Why should I wait till I completed this action before starting this action? For no reasons except lack of resources. So if I have only one processing resource, which is the case if you use a computer of the 60s probably, where there were no parallelism, there were no pipelining, then what's different? Then you have to choose one. And why don't you choose the first one? But if you have the possibility of starting more actions in parallel, you should actually do that. And this is actually the root of data flow analysis. People said, okay, and that's actually coming from compiling, it's not from testing or analysis. People working on compilers said, we can actually look at that and we can actually work on these three statements in parallel. So if we can say that there is no relation, we can actually walk through them. Now, of course, if I change this statement and if I actually have something like z is equal y plus x, okay? I guess it's clear to everybody that at this point I cannot have any parallel actions, okay? Is it clear to everybody? Okay, because, of course, I cannot start computing this before having updated this value, and I cannot start computing this before having updated this value. So this is the case where you do have a relation between the three statements. It's not just a relation of they are in the program in a given order, but it's more like they do actually require the value of the formula. So this is basically what data flow analysis is about. You have one relation which is the structural relation, which I try to suggest here, which is not important. Actually, it is important, and I maybe mentioned it. So it is important because if I have a loop, then it's actually so. It's not that you should completely forget about the structural relation. It's simply that you may want to actually consider some alternative to that, right? So there is some control relation which is important, but then there is also some other relation which is the flow of data, and that's where the name comes from, among different instructions. If data flow from one statement to another, these two statements cannot be sorted in any order, right? Now, how do you compute this relation formally? Okay, you compute two different kinds of sets. One is which is definitions and use. Okay, so the main principle is this one. You have two main actions about that you can do on the variables. One is to define the variable. Define means assign a value to. So you define x if you assign a value to x, and use is if you need. So use x is if you need the value of x for computation. Okay, so now let's see how do I actually what kind of definitions and uses here in this statement. So can you tell me which variable is defined and which is used in statement 1? X is defined and x. Okay, clear to everybody? Actually, just to make it, second one? Alright, and I can see. Okay, so this information is very easy to catch. Now, one question is, how do I actually Okay, one little observation is that actually this is not a concurrent definition that use of X, but it's a use followed by a definition. So when you do that analysis, of course, you have to consider the actual computation. So this is a statement that first uses X and then defines X. And this is actually the parameter. Okay, now I can spend half an hour to go through all the statements of Java and say this defines this, but basically it's easy to guess. The thing that you may actually consider is if you pass a parameter that's a use, if you return from a subroutine, that's the definition, and the one which is important is if X greater than Y. Okay, and this is a use of X and a use of Y. And actually there is a whole theory about what they call CUs and PUs, using comments and using predicates. Forget it. We don't have time, and we don't want to actually go through this. So that's the first step. So I take the program and I actually compute definitions and uses. Now, the second step is to chain definitions and uses. Okay. So what you want to do is basically this, which is, okay, I have a definition with this statement of X, and they have a use of X. Okay. They have a path that goes from the node where X is defined to the node where X is used. Okay. Okay. This is what is important. Why it is important? It is important in terms of what we do. It's important in terms of compiler construction, of course, because then this is a constraint of the order of execution of the statements, and it's a good input for program optimization. Again, we don't care about compiler construction today. We look at analysis or testing. It's important for analysis, it is important for testing. It's important for analysis because it tells you something about real interesting path versus non-interesting path. Let's get, for example, one information. I have a loop, okay? And I can execute the loop as many times as I want. How many times is a good number of times we can test the loop? Okay, 0 times, of course, because you always try the boundary condition. 1 time, of course, because it's in a boundary condition. The maximum number of times, if you have the maximum number of time, if you have it. And then it's better to execute it once or twice or 3 times. Well, the real information you get from data flow analysis is it really depends on the independence of the statements. Okay. If a loop, one loop execution, like one loop iteration, is completely independent from the former loop iteration, then there is no reason why you should actually execute it twice instead of once. Okay. So in that case, any number of execution of the loop is okay. But if the execution of the loop is actually, one iteration is actually constrained by the values computed in the former iteration, then it is important to execute twice. Okay. Now, this is a very simple thing. Now, let's consider a more complicated things like, well, I used to have this nice little problem of computing the maximum common division. The maximum common division by Euclid, which is basically when you compute the, you know the algorithm, you start with 2 numbers and you make the difference, and depending on which direction you switch. In that case, you have a loop structure which is basically like this one. You start, you enter, then you have some decisions, you do some actions, and then you actually join again, and then you actually go back and then you restart. Okay. And in general, you may have several different combinations. So in a larger problem, you may be that you actually do some other choices down here, and then depending on the choice, you may go back up here, or you may actually go down, or you may loop here, and so on. So, which are the paths? And you mentioned yesterday path testing. Remember? And we said, forget about path testing, because path testing is the kind of things that you have an infinite number of paths. You have to select some smaller set of paths. How do I do that? I mean, basically, I can say, look, I define a variable x here, I use a variable x here, I define another one times x here, I use it here, and then I define y, for example, and then I use y, and here I use both x and y. And so this gives you a better information about which pairs of statements should be changed or chained or not, and so which part of the loop should be repeated or not. Okay? Because this says if you use the value of x here, the result of this statement depends on this statement, depends on this statement. Okay? Because this statement may act differently if you actually get the definition here or the definition here, right? Because they may produce different values and they may impact on the use. Now, it's not only a matter of they produce a different value. It's also a matter they produce a different value according to a different logical assumption. So, let's say, I want to clarify this, you know. Let's say you get a value 10 here. Why the hell should not get a value 10 here? You know, why the hell this value should be completely different from this? Usually it's not, correct? Usually what you have is, probably this may not be able to produce any possible bad effects, but in general it can, you know. So if you have, like, say, let's talk about integers, you know. You may actually go ahead and get something better, but let's talk about integers. If you talk about integers and you have this huge amount of, you know, you have like all possible integers, in most of the cases a statement may produce any integer or something. And this one may produce any integer or something. So the difference is not in general in the set produced by. Okay? It is more like in I have a different logical reasoning behind the two different stages or the two different processes. So let's say for example, here I compute the index of the middle element in the array. Here I compute the index of the first element of the array, which is, you know. So even if the value can be any value, you know, the logical importance of the value is different. So if I expect here to use always the one by the last value of the array, and here I actually produce the middle, and here I produce the first, and here I produce another one. It's only when I get to use something which is supposed to be the last and is not that I may actually experience an error. Okay. So even if I cannot say that this value of this set of values produced by this statement is disjoint by this one, it may be logically different. And so it does make more sense to join this statement with this one or this statement with this one instead of, you know, for example, walking through a path. This, by the way, would actually result in some choices of the path, because if a definition comes inside the path and use comes outside the path, or both comes inside, means you must go at least twice through the loop. If they go to different branches, you might maybe go to different branches. So eventually it gets to a big interesting set of combinations of loops. Okay, is it clear so far? Sorry, I feel like I'm not here anymore to teach me the whiteboard instead of guiding by slides. Okay? Now, next step is, so far we have this concept of definition, this concept of use. Now we have a new concept which is DU path. Okay? Okay, we got this ugly picture. The idea that it is important to pair definitions and uses. Okay. Now we have one idea which is depth-free path. What is a depth-free path? Okay, so let me get one new picture just to. Okay, so I start here. I got a definition of x. Okay. Then I have another definition of x. Then I have a use of x and a use of x. And I have a loop. Right? Okay, so I can pair. Okay, I have a definition, I have another definition. Okay. So I compare this definition with this use, and this definition with this use. Okay. Now, pairing means I actually have one definition, one use, and one path, at least one path, that goes from the definition to the use. Now, let's see. Okay, let me add one node here with another definition of X. Okay. Okay. Now, how would I pair this definition with? Can I pair this definition with this use? Why?
Because there are definition.
Okay, great. So that's exactly the reason, the definition of that use path. Okay, the definition of that free path is I have a DU pair, so a definition use pair or definition use path. Only if I have a definition, I have a use, and I have at least one path from the definition to the use, such that there are no other definitions within the path. So I compare this definition with this use, I compare this definition with this use, I compare this definition with this use, I compare this definition.
No,
what?
no.
Bad design. Let me add one other note. That's okay. Assume I'm very bad for that. Okay, I compare that definition with that use. Okay, and this one with this use. Okay, so when you do diffuse analysis, what you do is you basically try to compute all the pairs such that you have at least one def use path between these two pairs. Okay. Now, how do I compute this? Okay. You know how to program or how to design an algorithm. Okay. Now, let's see if you have any clue. How would you actually compute this diffuse path?
Well, we take variable and look for the next operation that it will change this variable.
Great. So it says, let's start with X, see how many times I define X, how many times I use X, and then I change them. Is that what you're saying?
That was I was saying, but I'm not sure that it would correct.
You think it's correct then? Well, what are we going to do with branches?
Of course, we should keep in mind the branches, the loops.
Okay, so we have two classes of problems. One is branches and loops. It's not a problem really. So what you want to do is you want to build in the process you're suggesting you build a graph, a control flow graph, and then you actually look for the definitions, uses, and look for the free path from loops. So you do basically what I did. You're correct. I think you can imagine a program that does exactly what I did, what which is you start, you go through, and you look for, Okay, what's wrong with this program?
If some use is inside loop, then we can reach this use until by infinite number of ways.
No, because yes. Okay.
Okay. So if you have a branch, but the branch is achieved by reaching in some steps. Just he was saying, yes. And for example, you make 5 loops or 10 loops, some finite number of loops, and n plus 1 loop is the enrichment of the definition, which was in previous steps unreachable. Imagine. Well, I'll try.
Let me try to fix on his problem first, and then on your problem. But this is a small subtle problem that I want you to actually understand. Okay, sorry, I did it wrong. Actually, you're right. Yes, you're right. It's just that I was thinking of writing the solution. Okay, of course, if you have a definition, and then you have a use of the same variable, and then you have a stupid loop here. Okay, you have like the density passes from the definition to the use, from the definition to the use, from the definition to the use. Is that what you're saying? So you're saying that basically that yes, you're right, that you actually get the problem that you may have infinite number, infinite kinds of definition you can use terms. That's correct. Actually, you can limit that number because if all the paths are following exactly the same skeleton, there are little reasons where you can actually say, okay, I don't want that to do. You're right. So if you actually use the algorithm the way I actually suggested, you may enter an infinite loop because you may continue computing loops. But in general, what you do is, if you do not change the structure, the main structure of the control flow, you consider them as a class of algorithm. In fact, it does not make much sense in this case because you always reach the same definition. So what you really have is not. Technically, what you really have, this is not you have an infinite number of ways to go from this two-parent definition with this use, but you always pay the same definition with the same use. So it really depends on what you think about. So let me wrap up. The problem is you start with the definition, and you have an infinite number of paths from the definitions to the use. But if you compute, and then I should actually have mentioned that before, you have date use pairs and date use paths. Okay, so date use pair is the pair definition use of the same variable for which there exists at least one path. The date use path is a pair definition use and a path through them. So this is actually one single DU pair with infinite number of date use paths. So if you compute DU pairs and not DU paths, you would say, oh, but that's again the same, but that's again the same. And at some point you can actually cleverly say, if I don't change any arc in between, I stop. Okay, so your problem is a problem, but it's mostly a problem of my quick way of defining the things rather than the actual computation. Your problem, I think, has to do with feasibility of...
to repeat.
Yeah.
Well, imagine such a situation. You have a branch and some definition. Maybe it's a bad way of programming it, but no. Imagine a branch. So you have a variable n, and you have a definition of x in the branch when n is more than 10, for example. You have a loop, and
yes,
you have no definitions of x, any definition of x, until n is.
I see what you mean.
10.
So, okay. Let's see if I understood. So you were saying something like you start and you say, well, this is loop. Then you go here and you say if n greater than 10.
Well, 10 is bad because we can take some variable better.
Otherwise, then x blah blah blah, and this is actually modify and modify y.
Like that.
Yes.
How many loops we should make to ensure that we have a path?
Yes. So, do you understand? Everybody understand the problem? So, which is this definition is actually conditioned by this condition, and this condition may depend on other things. Okay. That's exactly what the second part of the problem. So, his problem was pairs versus paths. Your problem is static versus dynamic. So, this is a problem that you always have in all possible static analysis algorithms, which is you look at the structure of the code and you actually compute some information and you abstract from others. So one thing you abstract from in this case, you abstract from the actual value of variables. So I don't tell you what is the amount of definition, what do you define and what do you use actually. It's basically like, it's only, if x is defined, let me say it takes value 25, it's defined, that's it. The other thing you abstract from, and that's actually something that you have to do, is the actual value of the variables. And so you can't say this is true or this is not true. Okay? So what you can say is if you have a condition if, then you have a branch, and then you may or may not reach the definition, but you cannot say whether you can reach the definition. So in fact, it's even the problem is even worse, which is
it's better to say the worst. Well, isn't it better to say that we have a path that we haven't got?
Yes. So the even worse, it may be the case that you have a use of a definition of X on this path and the use of X on this path, and then you have, for example, a definition of X on this path, and for example, this is infeasible. It may be possible, but you'll never be able to go through this. So the diffuse path would actually compute this as a legal EU association, even if it's not. It is legal statically. So in your case, I would ignore the number of groups you need to. If you say, since there is a static path from the definitions to the use, there is a EU path or EU association. Okay? And of course, it may not be the case, but we actually walked through that yesterday. If you remember, when we talked about testing, we talked about structural testing a bit, for an example, and we said it is possible that despite the existence of a path or of a static chain of commas from one comment to another, some of the statement of some of the branches may not be executable. Okay, so this goes to the fact that this may be an infeasible EU path. Okay, and this may become an infeasible EU path. So, okay, maybe it's not completely clear, but I think it's a very interesting part to discuss. There is one problem, which is when we talk about criteria, we talk about criteria yesterday. One problem is to say, is this what are the criteria and the specifications? And the other one is to generate the test cases and execute the test cases. So, we get a very simple example, which is criterion. I identify statements. I want to execute all possible statements. Now I have the problem of finding the set of tests that do actually cover all possible statements. So one thing is to say, I can actually say, this is easy to say, it's difficult to compute. And sometimes it's impossible. And here they are after the same kind of thing. We compute associations, and then next is what we do with the association. So you're right. In the way I compute the association, since I ignore the value of a variable, I may actually end up in saying that this is a VU association, whether it is not, because the actual path is infeasible, or whether it is only if you can go 10 times through the loop under a given condition, and I can say that. So yes, what we compute is an approximation. Okay? Okay, so summarizing. First problem, we want to compute pairs and not paths. Second problem, we compute something statically, not dynamically, so we ignore the value of the variables. And so it may not be something that can actually be covered. Okay? It's useful anyway, but. Okay, third problem, which I guess it doesn't look so evident, unless anybody has an idea. Okay, complexity. Okay. I get, how many variables you have in a problem?
Depends on the scale of the problem.
Sure, but let's get it simple, let's say a reasonable problem. You have 2, 3, or 20, or 200. How many programs do we have programs with 2 variables? Programs that mean, let's say, okay, it doesn't make sense to, it doesn't make sense to analyze any size program, but this is actually analysis which is built into the compiler. Okay, so when you compile a program, do you expect to hold this set never more than 2 variables? Or 20, or 200, or 2000? In a program you have thousands of variables usually, right? Any idea how much it costs to traverse a graph? I don't want you to give me like the exact complexity. Is it logarithmic? Is it at least linear? Is it non-linear?
It has to be linear, but not the same thing.
It is, well, even if it's linear, it's bad. It's more than linear, usually. Okay, but let's assume that it's linear for the moment. In general, if you think about, if I give you like 1,000 lines of code, or so, I get a reasonable size graph. It's not a huge graph, it's a reasonable size graph. So I have, let's say, a graph with thousands of nodes, a couple of thousands. I gave you 200 variables, and then I give you the goal of writing a compiler which first does data flow analysis and behave with performances which are comparable with one that does not do data flow analysis. Would you go through this? I mean, the real question is that what we are discussing here is a conceptual definition, it's not an algorithm. Right. It's a conceptual definition because what you do is, yes, in principle, you take each single variable and you propagate the definitions and uses, and you see when they actually reach the definition of the other user. That's exactly what the algorithm did. You start, here is defined, go down, here is used, continue, here is used, then go down, and give a definition. So you propagate that. In practice, this would never work. It would take much more than a complete. Well, you know how much time, you know how compilers work? How many people took a compiler course? So it seems that this idea that compiler courses are always disappearing is common in most parts of the world. When I was a student, compiler course was required for everybody in computer science. Now it seems that everyone is not. Anyway, compilers are classified by the number of walks through the problem. You walk through the problem once, twice, 3 times. No, sorry, for the people who actually took a compiler course, this would sounds trivial, but but for the people who did not, Okay, so let's say historically the progresses of compilers are related to the possibility of incrementally analyzing the code and so reducing the number of walks through the programs. Because each time you walk from top to down to the program, it's a huge cost. Okay. And that's, so in fact, there are things like whether you can, how many of you use LaTeX? Do you know what LaTeX? Okay. Do you know why you have to actually run LaTeX and then LaTeX and then BibTeX and then LaTeX and then LaTeX because of only once? Is that any gnostic?
Because you have links and
references. Exactly. And this is exactly what the compiler's problem is. Think about it. Don't you think it is possible to write LaTeX, to improve LaTeX, to say, walk through once, build the references, check whether they're solved, walk through another time, build the bibref, check they're solved, walk through a third time. Is it possible?
Yes. You can run 35 minus 3.
Exactly. So it's very easy. So why people did not do it built-in in LaTeX? Very simple, because each time you walk through the whole program, it depends on the size of the document, of course. My book, which is over 500 pages in Fontaine, is actually written in LaTeX, So it takes time to do one pass through LaTeX. So it's not like, your little paper, you say LaTeX, in case, it's smaller. So you think about how, it's fast, but it's not that fast. Okay, now, that's exactly the reason, Each pass through a document takes time. So it is possible, actually there are many front-end tools or many scripts that actually do that for you, but the real reason not to do that built-in LaTeX is that you may actually don't want to do it because you want to save time. Compilers is the same class of stories. Walk through once, build the table like LaTeX. Walk through the second time, use the table. Walk through the third time, use the table that built from the table. And depending on how many times you walk through the program, it takes like minutes or seconds or tens of seconds or hundreds of seconds or minutes and so on. So, and the progresses in compilers were the same thing. Now, these analysis techniques started having been successful when they built into compilers. And what the people did is actually a sort of fixed point computation. So how many of you know fixed point computation? Everybody, yes. Okay. So I don't think I should actually go through the details of the argument, but I wanted to give you a very simple flavor about that, which is okay. Let me try to explain without giving the big formula. You know, and I give you the later the paper with the big formula, this big union of the gens and chaos. Instead of building the functions and uses, what people build usually are sets like gen set and kill set. Okay. So what is a gen set and what is a kill set? A gen set is basically what's called a generation set. So if you have a definition of n at a given node, so the gen set of n will basically be, in our case, the definitions. Okay? When you define, let's say, you walk through this node, and you have x is blah blah blah. It means you are generating some potential diffuse path. Okay? And then at the same time you are killing path that comes from that. Okay? So the same action is killing whatever comes before and is generating whatever comes later. Right? And what you do is you actually, once you actually get to the point where you actually use x, you know, you don't have to actually compute all the possible paths, blah blah blah. You just look at what is generated before. So, and I make it very, very short. You know, there are entire books on how to do data flow analysis. So don't think it's so simple. But I give you only the idea. If you're interested, you can actually look at that. What you do really in this case is you walk through the program and you can say at each node I can actually tell you statically what is the gen set and the kill set of length 1. Okay, which means what happens at that node. Now, and if you have a clue on how fixed computation works, what you do, you sit in the node and you watch the predecessors. And you say, oh, but, and let me draw it again because you know, I know that there are professors that are so nice and building up their nice whiteboards. I'm terrible. Okay, so let's assume that x is in the gen set of this node. And let's assume that y is in the gen set of this node. Now, the gen set of this node is whatever is here, plus whatever is here, unless killed before. Right? And the gen set of this node is whatever is here, plus whatever is here, minus the kill set in the node. Right? So, the very simple idea is I start one faster. Not even one factor. Build, let's say, logically, then you know you may actually have a better structure, you know, the node structure of the control flow. So you need really the structure of the control. You need the control structure because you walk through the control structure. You look at each node, what happened at each node, and then you actually walk back and say, you look at the former node and you add to the gen set of this node, or actually it's called the richer set, but I forget about that. What is on this node? And you do it for all nodes, which means after one of these steps, which does not walk through the graph, but only computes at each node on the basis of the predecessors, you actually get a set of gen set that says whatever is there and one node above. And then if you do it the second time, since you already got, so let's say, one x, y, z, k. Assume that this is actually the initial gen set. Okay? I look backwards. I would add x here because it's the former one, I would add y here, and I would add z here. Actually, you can do it even more clever if you actually do incrementally, but let's assume you don't do it incrementally. You walk back, okay? Next step, you don't add anything here because it's already fixed. You add x here and you add y here. And the next step, you don't add anything here and you add x here. And the next step, you don't add anything here, each. So at that point, you do not walk through the graph many times looking at different paths, but you just look at the predecessor and you stop when you reach a fixed point, which is you do not add anything anymore. And the complexity of the algorithm is not anymore walk through the whole graph, because it may be possible that the definition of the first statement be actually present the user the last statement. But you actually have a number of iterations which is comparable with the distance between the two parallel definitions and uses. Okay? Because you actually, here we went back 1, 2, 3 times, 4, depends on how incremental you are. But here you actually go through the set 4 times, because you have a distance 4 between the two nodes. If I take a key here, that's it. So I will stop not when I walk through the whole graph, but only when I walk through a small part of it, which depends on the distance between the things. So it's the least you can do. Okay, and at this point we can actually do interesting things, which is, and I'd like to get
the picture, so I can actually just write it, and then we actually
is a bit more, if you really love mathematics and not only intuition. Okay, you have a gen set, which is the set of variables such that V is defined or modified again. Okay, so basically, anytime you actually change the value of V is a gen. We have here V, which V is defined and modified as X up before M. Okay, it kills you. It kills you if you actually get to the point. So you will have this. You generate it here, and you kill it before that action. So you actually want to eliminate X from this set before that it actually is being defined. And then you have this idea, and you have to split it a bit. Actually, it doesn't have to be, because you have to decide. You can't actually update gen and keep in parallel. So you have this reach idea. You can reach the definition if it's the union of reach out of the predecessors. So whatever can reach this node is the union of whatever is reachable after the predecessor. And the reach out is actually what is reachable in the end, less the kills, plus a union the gens. Okay, so you start with a very simple distribution which is computed by looking at single nodes which are without walking through the graph. And then you actually, and this means incrementally up. If you actually have to build an algorithm, you actually do incrementally up, right? And then you can do several things. One is what is called reachability analysis or reach analysis, which is you really hear what you're after is a union, which means at least one. Okay, this is true if you can reach a node with a definition from at least one path, actually. right? And then you can actually generalize that and get the avail, which is what is available on all paths, okay? And availability on all paths is an intersection at this point, okay? And so one thing is to look whether you can come to this path, this node, through at least one path. The other one is if you can actually, whatever is available through all paths, okay? And you do that, again, you define generic here, you define what is the availability of the out, and then you intersect, instead of you actually, you get the union. So you start with all the variables, and you by intersection, you eliminate all of them, all the ones which are not really available, okay? And in general, you have four possible combinations. Okay? Let me tell you which are the combinations. You have at least one any path, which is a union. Okay? All paths, which is an intersection, can be seen reach in the veil. Okay? And then you have forward, looking at predecessors, and successors. Right? And so, reach analysis is the analysis that tells you what are the reachable definitions or the gen that actually propagate on any path, at least one, from the predecessors. Avail analysis tells you what are all possible paths, matters at least one path, predecessors, and you can actually reverse the graph, and instead of sitting on the top, sitting on the bottom, change the link, all the arcs, and watch bottom up, and get the backward analysis and look for the successors and see. And this is called live analysis, which is basically you sit in a node and you look from the backward what is still live once you are there. Okay? And then, well, this is the less interesting one because it's actually what is we cannot avoid. So, I don't think you actually got the whole picture yet, but I try to give you the essential information why you do that, and I try to give you the possible combinations. So, what I hope you understood is what is the essence of data flow analysis, which is basically pairing actions on variables, in this case, maybe other things, so that you actually can compute some dependencies among different elements. I hope you understood that it is static, which means I don't care or can take care of the value, after value of the variables, so feasibility is a problem. And the definition is a very naive algorithm that will not succeed, so you need to do something a bit more sophisticated, and you can spend one full course on how to build this algorithm, and it's probably worth it. And what you do is, instead of looking at single variables and propagating them, what you do is you actually compute sets of by computing a fixed point. And at the very end, what you have is a combination of different kinds of possibilities, depending on how many paths you consider, either at least one or all, and whether you walk from top to bottom or from bottom to top of the graph. Okay? And you get this information. At this point, you would actually work on you know, you actually understand what is actually the applicability of data flow. What do you do with data flow? Actually, there is much more, but I think it's not that important. What applicability of data flow is. What do you think is useful?
Problem optimizations, compiling, and some warnings about visual code, etc. So some diagnostics like malappointment, etc.
Okay, so yes, not only. Okay, so you can use these results in many ways. As analysis, and the compiler code will say you can optimize the code. For example, in many cases in a loop, okay, you may have some operation that would not really be affected by the amount of times you actually compute. For example, there are operations that are really, really important to be in the loop. Operations that are in the loop do not actually change if they are out of the loop. So compilers to data flow analysis can identify these operations and put them out of the loop. For example, it may be the case that in this sequence of operations, as we saw that said at the beginning, there is really no relation among them. Okay, and so you may actually resolve them to optimize the use of memory, for example, or to optimize the use of the pipelining computation which you have in modern computers. Okay, that's one part which we don't care because it's not the subject of this course. The second part is I can actually use that information, as you are familiar with, for understanding what happens on variables. So if I have, let's say, x at this node, and I have a use of x at this node, right? Having computed the diffuse pairs, it tells me, for example, whether there is at least one path from the top of the program to x such that there is no definition of x. Okay? And you see, any path. Okay? Or you can say whether there is, if you define x at this node, you can say whether there is, whether there are no paths that lead to the end with the use. Okay, so let's say if I use a variable x without having defined it before using it, it may be an error. We discussed already yesterday, it's not always an error, but maybe an error. If I define a variable at one point and I never use that value, it may be an error. Now, if you look at the compiler viewpoint, people will say, I can optimize. The compiler viewpoint, if you define and never use it, that's not bother changing the memory. Okay? If you look from the analysis or from the testing viewpoint, you may actually have used the wrong name variable. So one classic mistake that happens usually, and why it happens that you don't have the definition, you don't have the use. One thing which happens very commonly is that you have several variables which have similar names and you mistake the name of the variable. So you define one. Now, the example may be actually bad, but if you define x1 here, and then you actually use x here, meaning you want to use x1, this is actually a mistake. And it's not really an optimization opportunity, it's really a mistake. Now, by the way, this was a common case when people were Fortran programmers. Do you know why? Anybody knows Fortran? No. Wow. The dinosaur. Yeah, so Fortran 77 actually, so we're talking about the early Fortran, had a very nice feature which is given a maximum number of characters for the identifiers. I think it was 6 or 8, I'm not sure. 8? Yeah, I forgot about that. So now, if you look at the Java program, people have like, I don't know, invoices, and then they have invoice database. And if you look at the real, the instruction how to write with programs and how to write with variable names, you get these huge names, In Fortran, you have only 8 characters. So when I used Fortran to write my first program, we ended up having variables called x1, x2, x25, x2347, because there were 2 different things actually, was not x, was I. Fortran had Fortran 77 had 2 really nice features. One is small set of characters, and with 8 characters it doesn't look like, but it's really difficult to find meaningful names, variable, many different meaningful names of variables. Not because, you say, 8 characters, come on, it's 2 to 8. You have a huge possibility of selection, but you don't have that many selections in terms of, you go to a field and you use names, think about it, if you take the first 8 characters do an experiment. Take a program, take the first 8 characters of the variables, and probably you will distinguish 2 or 3 cases, because they all look the same, the first 8 characters. So you really need more than 8. Another one is Fortran actually have implicit typing. So if you start with IJKLM, then it's an integer, otherwise there is a real. So you could not say, like, for example, if you wanted to call your variable customer, no, please, because customer will be a real number. So unless you define it. So, well, that actually happens very, I had millions of problems. But if you think like invoices, small changes, and that's where data flow analysis can actually help. Not only, but can help definitely in that case. So one way you can actually use data flow analysis is really by walking through the program and getting a lot of information. Do you want to have a break between at the middle, which is already past, or you want to continue and... because I was trying to finish up this one, but I'll go up to the end. If you want to have a break, you should break now. Otherwise, you need a break. Yeah. Okay, even if it's not a good time for breaking, I think, if we go ahead a bit more, we will not break anymore. So let's break now.